Hey there, everybody. We're going to get started on recording the lectures for 3.9. This is doing derivatives of exponentials and logarithms. And this gives us, when we get to the last section, one of the coolest techniques. It's called logarithmic differentiation. So let's start off with exponentials. We're going to have f of x equals b to the x, where b is greater than 0 and x is any real number. If we look at the limit approach, we've got like limit as x approaches r of b to the x should equal b to the r. And I showed an example of like approaching 2 pi, doing 2 cubed is less than 2 pi, less than 2 to the fourth. And you can just keep narrowing it down. The book says b, capital B of x, not f of x. There's no reason for it. B is used in physics and stuff for other things, so I don't want to do that here. I'm going to just use f of x. We're going to assume that f prime of 0 exists, which means f of x is differentiable at x equals 0. That's the whole continuity thing. And then they use e to the x equal, or not e to the x equals capital E of x. In stats, that means expected value, and so I don't want to use e to the x either. I'm just going to stick with f of x for both of them. And we are going to take advantage of the properties of logs. If y equals b to the x, then x equals log base b of y. These are inverses. Okay. Okay, so let's take a look. We're going to start with doing E first, and then we'll switch to a generic B. If we do b to the x and we make be, we have e to the x. And so the inverse is going to be log base e. I don't know. Maybe I don't want to use this version right there. I'm going to do what we have up here. B to the x and log b to the x are inverses. Oh yeah, I wasn't, shit. Those weren't inverses earlier. Let me undo that. These are not inverses. These say the same thing. In fact, this is how logarithmic differentiation appears later on. So let me change that here. Not inverses, but equals. All right, these are the inverses right here. So we're going to do e to the x, and so the inverse of e to the x is log base e of x, and we write that as ln of x. I use the capital L, but almost everything shows this as this, not a capital L. And so I tried to use capital L for most of the times in these videos that we're making, but if I use the lowercase one is the standard. It just gets confusing when you're first learning it because you might think it's 1n and it's not. It's ln. ln means the natural logarithmic function. Okay? So we're going to go and do f prime is 0 for b to the x in general. If we do that, we've got limit as x goes to 0 of b to the x minus b to the 0 over x minus 0, which equals limit as x goes to 0 of b to the x minus 1 over x. And we're going to say as x approaches 0, this is approximately equal to that. Okay? It could, because it is. We don't have the techniques to show it right now, but it is. So if we apply that to a general f prime of x, we can do limit as h goes to 0 of b to the x plus h minus b to the x over h. And b to the x plus h does separate by the rules of exponents to b to the x times b to the h. And we're going to factor out of b to the x here. So we got the limit as h goes to 0 of b to the x times b to the h minus 1 all over h. Now, b to the x is not a function, or it doesn't have an h in it, so we can actually pull it out. And so we have b to the x times the limit as h goes to 0, b to the h minus 1 over h. And we just showed that this is approximately that. If I just replace the x with h, we have that there. So we're going to have f prime of x equals b to the x times f prime of 0. We apply this to a general one. If we do b, not general one, if we do b equals e, f prime of 0 equals 1. So f prime of x equals e to the x. Okay? So if you start with y equals e to the x, dy dx equals e to the x. It's the only function where the derivative of e to the derivative of itself is itself. That's super fucking cool. I don't know about you, but it's super cool. Chain rule does apply if we have g of x inside the function, like e to the g of x. When we take the derivative, we still have the e to the g of x, but then we take the derivative of the exponent. Okay? So kind of like e to the 2x. When we take the derivative, we've got y prime equals e to the 2x times d dx of 2x. Y prime equals 2e to the 2x. All right. Let's check this out. We're doing something else up top. F of x equals e to the sine of 2x. So when you take the derivative, you have the original function, f prime of x equals e to the sine 2x. Then we use the chain rule. So the derivative of sine 2x is cosine 2x times 2, and it condenses down like that. Another way of doing this is saying u equals sine of 2x. So du equals, or du dx equals cosine 2x times 2. I'll put the 2 out front. And we're doing d dx of f of u equals d dx of e to the u, which equals e to the u du dx. And if we plug the things we had back in, you see that we get that. If you like the u substitution method, it's worth taking a look at. I'll do it again on later ones. Let's take a look at doing e to the x cubed over x squared. I set this up as a quotient rule. We have e to the x cubed on top. So if we take the derivative, we got to do the chain rule. We have e to the x cubed, and then the derivative of x cubed is 3x squared. Low is x squared, so the derivative is 2x. And when we go through the quotient rule, we have low times the derivative of high, so x squared times 3x squared e to the x cubed. Then we have minus high times the derivative of low, so minus e to the x cubed times 2x. All over low squared, so x squared squared. Over here on the right, I factored out a common factor out on top. Factor out x e to the x cubed. And I see that I have x's on bottom, so I factor out an x on bottom. So we'll see that those two cancel. And when they cancel, we get f prime of x equals e to the x cubed times 3 to the x cubed minus 2, all divided by x cubed. All right, I want you to give it a try on this one. If f of x equals x to the 4th, e to the 7x, find f prime of x. Pause the video and see what you get. All right, I'll assume you did. This is a product rule, so we're going to take the derivative of x to the fourth and leave e to the 7x alone. And then we add it to x to the fourth times the derivative of 7x, e to the 7x. Okay? When we do that, we've got 4x cubed times e to the 7x plus x to the fourth times 7e to the 7x. And if we factor out a common factor, x cubed e to the 7x, it looks a little smaller. X cubed e to the 7x times 4 plus 7x. Okay? Examples where this comes up in life, population growth is often modeled by exponentials. Let's say a mosquito. Now, let me pause this real quick. Oh, stupid spam calls. I hit the ringer off. We're going to say a mosquito population is represented by the function a of t equals 1,000 times e to the 0.3 t. Exponentials are often used for modeling population growth. Okay, and that shows the population after t days. So what is the rate of change after 4 days? The rate of change will be the derivative. So we'll take the derivative of that. The 1,000 is just a coefficient. The derivative of e to the anything is itself times the derivative of the exponent. The derivative of the exponent here is 0.3. And if we multiply the 0.3 times the 1,000, we get 300 e to the 0.3t. That's for any day t. When we plug in t equals 4 days, a prime of 4, we get 300 times e to the 1.2. It's approximately 996 mosquitoes that day. That's the growth rate. So mosquito population is blowing up pretty quick. That seems a little high. I don't know if that's a realistic number. And there are other things in population growth where they change the function to have something else with it to give it like a population cap. But that's another day. That's an example of doing stuff here. Next video will be derivatives of log functions rather than exponentials.